We're going to start chapter 7 today, and the first section is an intro to exponential functions. So chapter 7 is all about exponential and logarithmic functions. So first we're going to talk about exponentials. So an exponential function is a function with this general form, y equals a times b to the x. Now remember order of operations, the exponent has to go to the b to the base first before getting multiplied by a. There are a couple of restrictions here to an exponential function, and that is that a can't be 0, because if a was 0, the whole thing would be 0, so that wouldn't make sense. B has to be greater than 0, so we do not put negatives in there, at least not in exponential functions. And b can't be 1, because if b was 1, 1 to any power is 1, and then this, again, would not be exponential. Okay, so first we're going to start with a graph. So y equals 2 to the x. So I have this table here that's partially filled out. So these are the x numbers that I'm going to use, and I'm going to plug them into my function y equals 2 to the x to get my y values. So I put in -3 for x, and I get 1/8. Now, you might be like, wait, what, lady? So this would be 2 to the -3. And remember, a negative exponent makes things go on the bottom. And then that becomes 1/8. Okay? 2 to the -2 is 1/4. 2 to the -1 is 1/2. 2 to the 0 power, remember anything to the 0 power is 1. 2 to the 1 is 2. 2 to the 2 is 4. And 2 to the 3rd is 8. What I might recommend doing, though, is starting at 0 and doing all of these first, because these are a little easier. And then once you get these values, you can look up here. This is 2, that's 1/2. This is 4, that's 1/4. This is 8, that's 1/8. So that might be easier for you than starting with the negatives. I actually usually start with 0. I don't know why I didn't just then. Okay, so now we're just going to graph these. We're going to see what it looks like. So I'll give you a minute to get your points on here. But again, I would start with 0, 1, because that point's easy. And then 1, 2, 2, 4, 3, 8. And then, I mean, these are fractions, so you don't have to get, too crazy. Just, make them get smaller as you head toward the left. And then try to connect it with a smooth curve. And it's very important right here that this doesn't touch the x-axis. We're going to talk about that more in a minute, but while you're drawing your first one, I just want you to know that it does not cross the x-axis. Okay, let's try another one. So over here we have y equals 1/3 to the x. So let's do what I just said this time. So let's put in 0 for x first. So 1/3 to the 0 power, well, anything to the 0 power is 1. 1/3 to the first power is still 1/3. 1/3 to the second power, so let's think about that. 1/3 to the second, that equals 1/9. That okay? And then 1/3 to the third power would be 1/27. Okay, let's do that in reverse. So now we have, let's look at this -1. So we have 1/3 to the -1 power. But anything to the -1 power is just the reciprocal of itself. So we have a 3. So again, but it's backwards from example 1. But see, the 1/3 turned into a 3. The 1/9 is going to turn into a 9. And the 1/27 will turn into a 27. Oops. Gave it away. Okay. So let's get our graph going here. First, I would suggest plotting the point 0, 1, and then negative 1, 3, negative 2, 9. Now, if you notice, I didn't actually graph negative 3, comma 27 simply because it was never going to fit on the graph. So I just didn't include it. And then going to the right, 1, comma 1/3, 2, comma 1/9, 3, comma 1/27. And again, you don't have to get crazy. You just want to make sure that these points, you know, are getting closer to the x-axis, but are not actually touching them. Okay. All right, so let's look at what's going on here. So first thing here is neither of these touch the x-axis. Exponential graphs, unless they're transformed like shifted, they're not going to intersect the x-axis. And what that's called, because you can see that they get close to the x-axis, that's called an asymptote. I don't know if we've ever talked about that word, but an asymptote is a line. Well, it doesn't have to be a line, but it's generally, well, for our purposes right now, it will be a line. An asymptote is a line or a curve that another function approaches but does not reach. So on this first one, if you're traveling on this graph to the right, to the left, which we don't normally do that, but as we go to the left, this is going to get closer and closer to the x-axis, but it won't ever touch the x-axis. But think about that. This is 2 to the x. Even if I put in a number like negative 1,793, I'm still never going to get 0 for an answer. I'm going to get very close to 0, but I'm not actually going to get 0. I can't get 0 from an exponential function, and that's why it doesn't intersect the x-axis. That's why there's an asymptote at y equals 0. We usually write asymptotes as dotted lines to sort of indicate that the graph doesn't touch that line. So that's normally what people do. Okay. So what else do we notice about these graphs? So in the first example, this is B. If we go back and look up here, see it matches B. B is 2, and in this one, B is 1/3. So let's look down, let's look at the graphs. So for 2 to the x, as you travel on the graph from left to right, it increases. But on example 2, when you travel to the right, the function decreases. And that's because of the size of these numbers, 2 and 1/3. So when B is greater than 1, it's an exponential growth graph. If B is less than 1, but greater than 0, because remember, B has to be greater than 0. So if B is basically a fraction, which is, that's really all that says, is really that it's a fraction, then that's exponential decay. So that means that the y values, whatever they represent, are decreasing over time, but in an exponential way. Okay, let's talk about the domain. There are arrows on the ends of these, on both. Right here, I need a new color, this is boring. This is pointing to the left, this is pointing to the right, this is pointing to the left, this is pointing to the right. So to me, that's indicating that the domain for both is all real numbers. Let's talk about the range, though. The range, it's pointing up on this 2 to the x, but it's not pointing down on this, on the left side. It's just pointing over. And we discussed just a minute ago that 2 to the x was never going to equal 0. So the range then is 0 to infinity. Although I realize now I made an error. That should be round because it never hits 0. Sorry about that. I always catch mistakes after the fact. And that's true for both of them. They're only above 0. So the range is 0 to infinity. And the y-intercept, which we didn't really talk about, but so that's here and here. If you notice, they're both 0, 1. It's not always 0, 1, though. Really, the y-intercept is 0, comma a. So that's whatever this number is here. But in our examples, there wasn't a number here, so there would be an invisible 1. But so that's why the intercept is at 0, comma 1. But I really want you to think about it as 0, comma a, so whatever that a number is. Okay, let's look at example 3. So let's identify the exponential growth or decay. So just looking at the equation, not a picture, decide if it's exponential growth or decay. And then we'll find the y-intercept. So let's think about this. We have y equals, oh, you didn't see that. Y equals 12 times 0.95 to the x. So two things you want to keep in mind here. This is A, and this is B. Okay, B tells us whether it's going to be growth or decay. So come up here. So if B is greater than 1, it's exponential growth. But if it's a fraction, then it's decay. So a fraction, well, we have 0.95. That's a fraction. So that means this is going to be decay. And A is, so decay because B is a fraction. The y-intercept is found from 0, comma a, so that's going to be 0, comma 12. All right, let's look at the second one. 0.25 times 2 to the x. So A is now this number, and B is this number. So B is bigger than 1, making this growth, and the y-intercept is still going to be 0, comma a, so 0, comma 0.25. Okay, so you got to be able to recognize that just from the equation. Okay, let's take an example here. You put $1,000 into a college savings account for 4 years. The account pays 5% interest annually. So we're going to, again, find if it's exponential growth or decay and find the y-intercept. So if you're putting money into a savings account, that means that you are, saving money, so you're getting more. So this should be growth because you're saving money. It's not like a loan or something. So here I have growth because savings accounts grow. Okay. B is 1.05. Now, you might be like, wait, where'd the 1 come from? But if you're increasing in a percentage, it's 1 plus the amount of, or the rate of increase. And that's greater than 1, so therefore it would have to be exponential growth. Okay, what else? The y-intercept. The y-intercept would be 0, comma a. But let's think about what is a. I don't have an equation here. So the y-intercept is the initial amount, which is true even in lines. Your starting point is your y-intercept. And that's also true here. So because 1,000 is the initial investment, A is 1,000, making that the y-intercept. Now there's this other thing over here I want to point out. Do you see how B is 1.05? That has a special name, and that's called the growth factor, or it would be called the decay factor. So the growth or decay factor, as opposed to the growth or decay rate, is either 1 plus or 1 minus. So let's write that over here. I didn't write it before, but I probably should have. So growth factor is 1 plus, growth rate. And the decay factor would be 1 minus, it wouldn't be growth, the decay rate. Yeah, that's good. That's better. We should have that written down. Okay, we're going to talk a little bit more about interest here. So here we have a simple interest equation. So this is a of t equals little a, they have different meanings, times 1 plus r to the t. And let's write down what all of these things mean here. So capital A is the amount after some number of time periods. So it's like a final amount. Lowercase a is the initial amount. R is the rate of growth or decay, not the growth or decay factor, but the growth or decay rate. And T is the number of time periods. Usually it's years, but it could actually be anything, but so that's why I put number of time periods. Okay, so let's look at example 4. You invested $1,000 in a savings account at the end of 6th grade. I don't know why that's important, but that's okay. The account pays 5% annual interest. How much money will be in the account after 6 years? So it doesn't look like it's compounding except for just every year. So that is something you want to look for that we're going to discuss more in the next section. So we are going to use this simple interest equation here. And basically they want us to find a of 6 because they want us to find out how much money will be in the account after 6 years. So that's why I have the question mark here. And then over here, I have A, R, and T. Those are the things that are given in the equation. So I just like to make a little list of what I got going on here. So lowercase a is the initial amount, so that's going to be 1,000. The rate, that's the 5%, but you have to write it as a decimal, so that would be 0.05. And T is the number of time periods, or in this case, years, so that would be 6 years. So we're going to take all of these numbers and we're going to plug them into our equation. Like so. And then we would type that in our calculator and we get $1,340.10. So that's how much you have. That's how much you have at the end of the 6 years. So 1,000 of this is how much you put in. And then the extra $340.10, that's how much you got from the interest. Not bad. Although try to find a savings account with 5% interest. Okay, that's it for section 1. Section 1 is kind of short. Section 2 is kind of short too, but it's okay. It's the first week back from spring break, so maybe we shouldn't push it. Okay, so make sure that you upload your notes and make sure that you try the homework problems and feel free to come with any questions.